So let us continue that problem of design of RCC silo. So in the last class I have explained about the design of the silo wall. Now we will continue with the design of upper bottom for the same data. So design of upper bottom of silo. So you know that cylindrical silo will be like this. So in this problem I have taken wheat as the material. So this portion, this is the wall. So already I have explained the design of wall. Now we will take up this design of this upper bottom. So the dimensions in this problem already it is given that this internal diameter is 5.5 meter and this opening is 0.5 meter, so that the center line distances, so this becomes 2.75 meter, and of course this inclination is 45 degrees. So all these I have given in the last video, all these details. Now we will see how this upper bottom portion can be designed. So for that we have to calculate the loads coming on this upper bottom portion. So load on this upper bottom portion, you know that it comes from the cylindrical portion as well as this conical portion. So you have to calculate the loads coming from these two portions, and unto that we have to add the self weight of this upper bottom also. So there will be three loads acting on the upper bottom. Now the thing is, the load on the upper bottom will be maximum during filling. So that condition you should know. Load is maximum during filling. And in the problem it is given that this value of mu dash, that is coefficient of friction between the wheat and the concrete wall is mu dash, that is tan inverse of, during filling we have to take it as tan inverse of that is tan of 0.7 times, 0.7 times this phi. So phi is the angle of repose on that wheat, which is given as 28 degree. Okay, so that means it becomes tan of 0.7 into 28 degree, which comes out to be 0.384. So the value of mu dash, coefficient of friction between the wheat and the concrete wall is 0.384. Now and also the pressure ratio is given as 0.5. K value is given as 0.5 in the problem. Now we have to use that Johnson's equation to compute the horizontal and vertical pressures. So I will take this horizontal pressure equation, Johnson's theory. The horizontal pressure on the upper bottom is given by pH is equal to gamma, that is the same equation which we have used earlier. So that equation is given by pH is equal to, so let me write the equation, gamma d by 4 mu naught, 4 times mu naught into 1 minus e to the power of minus 4 times mu naught k divided by d into h. So this is the equation. So here all these values you will be knowing. So gamma is 8.5, that is the density of wheat, 8.5 kilonewton per meter cube, it is given in the problem. Mu dash, of course, I have to take 0.384, 0.384, and this diameter is here. So since I am taking only this portion, only for the upper bottom portion, so I will take this value of D of course it is 5.5 meters given in the problem. Internal diameter D, this is D, and then K value of course 0.5. H value is the height, total height of the cylindrical portion, which is 80 meters. So this is H. This is H. Now, if you substitute all these values in this, and if you simplify, you will be getting 3H value as 28 kilonewton per meter square. This is the horizontal thrust or the pressure. So now we have to calculate the load on this upper bottom. So of course pH will be acting like this. This is pH, whereas PV will be acting like this. Now by knowing this K value, pressure ratio value, we can get the value of PV as pH divided by 0.5. Because pH by PV is 0.5, this K is nothing but pH by PV, ratio of horizontal pressure to vertical pressure. So now if you use this 28 divided by 0.5, it comes out to be 56 kilonewton per meter square. This is the vertical pressure on the upper bottom. This is the upper bottom portion. On this, the vertical pressure is given by this much. So we can calculate the load now. So from pressure we can calculate load by just multiplying by the area. So the total area now here. So load, we can write load on the upper bottom from cylindrical portion. So as already told, there will be 3 loads. So from cylindrical portion, from the conical portion, and self weight of upper bottom. So all the 3 we have to add. So this is given by whatever PV we got, 56 multiplied by the cross sectional area of silo, pi by 4 into 5.5 square. So this is the value. So almost 1330 kilometers. So this is one load. Then we have to calculate volume. Volume we have to calculate. So volume of upper bottom. Volume of upper bottom. Which is given by that that conical portion volume we have to take. 1/3 of pi into. So this is the conical portion. Half I have to take. From that I have to take this opening. So if I take half portion, one portion if I take this portion, then it will be half of this 5.5 will be 2.75. From that I have to deduct this 0.25 meter radius. So here it is now it becomes pi into 2.75 cube. This is the formula for a cone, volume of a cone. Pi into 2.75 cube whole cube minus pi times half of that will be 0.25 whole cube. So if you simplify this, you will get 21.76 meter cube. So this becomes the volume of this upper bottom portion, one side portion. So like this, if you take this silo like this in plan. So one side, so there is an opening here. So you are going to take you will be having the volume of this portion. This is the circular portion, that is upper bottom portion. So in this volume of that, of course only half the portion I have to take, only this much. So whatever wheat is stored in this portion, so because this is 0.5 meter opening and this total force diameter is 5.5. Okay, so only whatever this upper bottom portion is this much. So whatever load is acting on this one side upper bottom portion, we are going to calculate. So how we are going to calculate? So we know the volume now. When the volume is multiplied by the density, you will get the weight of wheat in the upper bottom portion. This is from cylindrical portion. This is first load. Second load will be weight of wheat, that is the grain, in upper bottom portion. In upper bottom portion, this is given by whatever volume we got, 21.76 multiplied by density of wheat, which is 8.5 kilonewton per meter cube. So this will be in meter cube. This will be in kilonewton per meter cube. If you multiply 184.94 kilonewton. So this is the weight of wheat in the upper bottom portion. Second load. Now we have to calculate the self weight. So self weight of upper bottom. Self weight of upper bottom. So for that we have to assume thickness. So let us take the thickness of upper bottom, minimum thickness 150 mm. 150 mm is the thickness we are going to assume. So mean diameter I will take. So let us not consider the minimum or maximum diameter. I will take the mean diameter. Mean diameter will be mean diameter of that hollow, that is upper bottom, is given by. So I will take 5.5 by 2 plus 0.15 is thickness into root 2. This is the mean diameter. If you simplify this, you will get 2.96 meters. 2.96 meters as the mean diameter. Then thickness, of course, 150 mm means it is 0.15 meter. 0.15 meter. Now I have to calculate the sloping length. So this is the sloping length, upper bottom sloping length. So the sloping length is given by, since it is at an angle of 45 degrees, this sloping length is given by total diameter minus opening divided by 2. For one this thing, divided by 2, which comes out to be 2.5 meters. So this sloping length is 2.5 meters. Okay. Now we have to calculate the volume of concrete. Volume of concrete in that upper bottom portion, which is nothing but pi into mean diameter, that is 2.96 meters, into thickness into 2.5. So 2.5 is sloping length. So length multiplied by thickness multiplied by the circumference. So pi into d, circumference. So this comes out to be 3.49 meter cube. When this 3.49 meter cube volume of concrete is multiplied by the density of concrete, so you get the self weight of upper bottom. So self weight of upper bottom is equal to 3.49 volume multiplied by density, that is 25 kilonewton per meter cube for concrete, 87.25 kilonewton. So this is the third load. So we have had all the three loads now. The first one is load on the upper bottom of the cylindrical portion. Second one is weight of wheat in the upper bottom portion. Third one is self weight of upper bottom. If you add all these three, you are going to get total weight on the upper bottom. Total weight on the upper bottom, on the total load on the upper bottom. So which is nothing but equal to 1330 plus 184.94 plus 87.25. So it comes out to be 1602, roughly 1602 kilonewton. 1602 kilonewton. Okay. Now from this, we will take this as W. Upper bottom has to be designed for direct tension. I have told in the beginning, direct tension. The direct tension which is acting on the upper bottom during filling is given by W cosecant theta. If you resolve the force W, so this upper bottom has to be designed for direct tension. So I will write here. So direct tension force I have to calculate now, which is given by W cosecant theta, where theta is 45 degree. This angle of inclination, this is theta. So now whatever load is acting on this upper bottom, total load W. Okay. So it has to be, this has to be resolved and it has to be designed for direct tension force. This direct tension force, if I take this as theta, so direct tension is equal to T W cosecant theta. So theta is 45 degrees and W is like total load 1602. So I will take this as 1602 into cosecant 45 degrees. That is root 2. Cosecant 45 is root 2. So it comes out to be 2265.6. Yeah. So this is the direct tension force for which that upper bottom has to be designed. Now direct tension per meter width we have to calculate, because reinforcement we have to calculate per meter width. Direct tension per meter width, so which is 2265.6 divided by circumference, pi into d. So this is pi into 5.5. So which comes out to be 131.1 kilonewton per meter. Okay. So therefore AST required, we have to calculate for this one, because we are providing like slab. Per meter width we have to calculate the reinforcement required. So AST required is equal to 1.5 times this we have to take, 1.5 into 131.12 into 10 cube divided by 0.87 Fy. So 0.87 Fy is 414. So this is what we will get. So it is this one, 10 cube is nothing but the V value, that is 1000 mm. So the value you are going to get is 554.75. 554.75 millimeters square. Actually here, this whatever we got 131.12 kilonewton per meter is the same as 131.12 newton per millimeter. So that's why we are taking the same value there. So in the expression for AST required, the value should be newton and millimeters. So we have got AST required this much. If you use 10 mm diameter bars, 10 mm dia bars, so the spacing required will be equal to, so pi by 4 into 10 square, that is area of 1 bar, divided by reinforcement, that is 554 4.75 multiplied by 1000, that is for 1 meter length of the hopper bottom. So it comes up to 144 mm or 144 mm. So that means we can provide it 140 mm. So say 140 mm. You can know it now. So 10 mm dia burst, center to center 140 mm is provided to resist that direct tension in the hopper bottom. So that is the reinforcement required in the hopper bottom. Next we will design for hook tension also. So we have to design for hook tension. So this is for direct tension. Hook tension is also called as circumferential tension. Okay. So for that also we have to design. Design means you have to find out the spacing of the bar. That's all. Same 10 mm diameter assume and you can find the spacing. So design for hook tension. So when you are designing hopper bottom, you have to design both for direct tension as well as hook tension. Design for hook tension or the circumferential tension. So that reinforcement is provided like this. So this is the upper bottom portion. If I take, this is the opening. So your hook tension reinforcement will be provided like this. Okay, this is hook tension. Yeah. Now, how to do that? Let us say. So since we are designing for this portion, only half portion, in the upper bottom. So I will take this mid height of conical bottom. So that means from here, mid height. So this is the midpoint of this thing. So this is 18 meter. So I have to add half of this 2.5 to this. So that means from here to here it becomes 18 plus half of 2.5. 2.5 by 2. It comes out to be 19.25 meters. So let us right here at mid height. At mid height of conical bottom or hopper bottom. So the value of h becomes 18 plus 2.5 by 2, that is 19.25 meter. 19.25 meter. So diameter D will be 5.5 plus 0.5 by 2. So it comes out to be 3 meters. Now by using the same Johnson's theory, that pH value you can find out. pH value you will get that here in this case, if you substitute everything and simplify, 16.48 kilonewton per meter square. You can use the same formula, substitute for mu dash, K, all those things, H everything. H is here 19.25. Substitute for everything and simplify everything, pH is much. So PV will be pH divided by K, where K is 0.5. This K value is 0.5, therefore it becomes double of this, 32.96 kilonewton per meter square. This is the vertical pressure, this is the horizontal pressure. Yes. Now self weight of this thing, that upper bottom, it is 0.15 thickness multiplied by 25. So it comes out to be 3.75 kilonewton per meter square. So we have to calculate what is called as this normal pressure acting on this portion. Normal pressure acting on the portion. Normal pressure. This normal pressure is given by Pn. I can write as Pn. Pn is given by PV cos square 45 cos square 45 degrees plus PH sin square 45 degrees. That is theta plus Ws cos 45. So better you remember this formula. 45 is the theta angle. Theta is this angle. So if you substitute these values pH, PV and Ws here and simplify, you will get the normal pressure as 27.375 kilonewton per meter square. Substituting these values and simplifying, you will get that much. Now mean diameter at the center of the sloping slab. So normally you will take at the center. So therefore direct tension also we take at the center. For hook tension also we take at the center. So mean diameter at the center of sloping slab. Mean diameter at the center of sloping slab will be 5.5 plus 0.5 divided by 2 plus 0.15 into 2. This is the mean diameter. So if you simplify this, you will get 3.21 meter. 3.21 meter mean diameter D. Now hook tension is given by hook tension is given by 0.5 times this 3.21 into 27.37. This is the value. Of course, it is per meter. So it is given by 43.96 kilonewton. This is in kilonewton per meter. So this is the hook tension for which the reinforcement has to be designed. So ASP required will be 1.5 times this 43.96 into, of course, for 1 meter length that is 10.3 divided by 0.87 Fy. Fy is 4 meter. So if you simplify this, you get 182 millimeter square as the scale required. Okay, so this is what we get. Now at the junction with ring beam, H is 18 meters. So this is at the junction here. Ring beam will be there here throughout. So at this junction, so what is the reinforcement? We have to take H as 18 meters, whereas here the H value is, for the earlier case it is 19.25 meters. That is at the mid. So we are going to calculate the hoop reinforcement at the mid of the copper bottom as well as at the junction here. So it will be different here. So if you substitute the same using Johnson's theory, if you substitute and simplify, pH, PV values here, pH value we are getting 28 kilonewton per meter square. This we have done earlier, so you can just have the same value here. Earlier we got this value, so those values we can use here, 56, and of course Ws is same, 3.75. So use the same formula, this formula only. So you will get the Pn value as 44.63 kilonewton per meter square. So here it is more. So normal pressure is more here at the junction compared to this value, compared to this point. Now if you calculate the diameter here, diameter is also different here, mean diameter 5.5 plus 0.15 times into, it is 5.71 meters. That is the diameter, mean diameter. Now, if you calculate the tension force P is given by 0.5 times this 5.71 into 44.63. That is the direct tension force or T value, not direct tension, hook tension force. So hook tension force is given by 0.5 times 5.71. T is equal to 0.5 into 5.71 into this, that is 44.60. So this is the value in kilonewton per meter. If you simplify this, you will get 127.48 kilonewton per meter. So this, for this the AST required can be calculated. So once again the formula is same. AST required is 1.5 times T, that is 1.5 into 127.48 kilonewton per meter is the same as newton per mm. Okay, into 1000, that is for 1 meter length, divided by 0.7 fy, 0.87 fy, that is 0.87 into 415. If you simplify this, you will get 530 millimeter square. Of course, here also assuming 10 mm diameter bars. So at 140 mm center to provide, that will take care of this. So we have got the same reinforcement here also and here also. So that means we can provide throughout the same quantity of reinforcement. And lastly, you can draw the sketch of reinforcement. So like this. So this is the wall portion and this is the upper bottom portion. So you can always have the diagram like this. Half of the diagram we can show because it is symmetric. So we have got the wall reinforcement like this. Of course, to detailing I am not doing. Just I am showing the bars how they are placed. So in the wall as well as in the upper bottom. So this is the wall reinforcement. Torque 10 at 170 mm center to center. And coming to this reinforcement, that is here in this, it is torque 10 at 140. Torque 10 at 140 mm center to center. Just we have got, of course, at the bottom we can curtail. At the bottom we can curtail so that because the reinforcement is the value of T is very less at the bottom, we can curtail here at the bottom, so you can provide torque 10 at 280. That means you can double the spacing at the bottom. So this is how the design of silo is done. So of course it is electric design. We have to design the cylindrical wall as well as the upper bottom. So for that we have used Johnson's theory to calculate the horizontal pressure and vertical pressure acting on the wall as well as acting on the upper bottom. So in the design of upper bottom, we have to consider three loads. Load of weight, that is grain load coming from the cylindrical portion, and grain load which is connected in the upper bottom portion, and also the self weight of upper bottom. For that we have to design the reinforcement, and we have to design the reinforcement for both direct tension as well as hook tension. Okay.